Hi students, our topic is response of critically damped second order system for unit step input. In the previous classes, we have discussed about second order systems and we are discussing its response to unit step input. Now we will discuss about the response of critically damped second order system for unit step input. So first of all, we know that in the case of a second order system, the response or the transfer function will be C of S divided by R of S is equal to omega n square divided by S square plus 2 delta omega ns plus omega n square. You should by heart that equation. In the case of second order system, the standard form of closed loop transfer function is equal to omega n square S square plus 2 delta omega ns plus omega n square. So for critical damping, the value of delta will be equal to 1. So we can substitute the value of delta in the equation for C of S by R of S. So we will get C of S by R of S is equal to omega n square divided by S square plus 2 delta omega ns plus omega n square, and here the denominator is in the form of A plus B all square. So we can write it will be equal to omega n square divided by S plus omega n all square. Here we know that the input is unit step, that means R of t equal to 1. So its Laplace transform will be equal to 1 by S. Then the response in S domain, that is C of S equal to R of S into omega n square divided by S plus omega n all square. We can substitute the value of R of S. So we will get 1 by S into omega n square divided by S plus omega n all square. So that will be equal to omega n square divided by S into S plus omega n all square. So we got the Laplace transform of response. But actually we want to find out the response in time domain, that is we want to find out it C of t. So we have to take the inverse Laplace transform and we can split the terms by using partial fraction methods. So we can write by partial fraction expansion, we can write C of S is equal to omega n square divided by S into S plus omega n all square, and that can be written as A divided by S plus B divided by S plus omega n all square plus C divided by S plus omega n. Next we have to find out the value of A, B and C. We know that A will be equal to S into C of S at S is equal to 0. We can substitute for C of S so that S and S terms will be cancelled. You can see here. See, S and S terms will be cancelled out. So rest of the terms will be omega n square divided by S plus omega n all square at S is equal to 0. And here you can substitute the value of S into this equation so that you will get omega n square divided by omega n square equal to 1. So next is we want to find out B. That means B will be equal to S plus omega n all square into C of S at S is equal to minus omega n. That is equation for finding out B. And we can substitute the value of C of S, and so that S plus omega n whole square terms will be cancelled out, and finally we got omega n square by S, and we have to substitute S is equal to minus omega n, so we will get B will be equal to minus omega n. Next we want to find out C. We know that C can be found out by using the equation d by ds of S plus omega n all square into C of S at S is equal to minus omega n, and here S plus omega n all square terms will be cancelled out, so that we will get d by ds of omega n square divided by S at S is equal to minus omega n, and the derivative of that term will give minus omega n square divided by S square, and we can substitute the value of SS minus omega n, so we will get minus 1. So we can see we got the value of A, B and C, so we can substitute in C of S equation so that we will get the equation like this, that is equal to C of S will be equal to A by S plus B by S plus omega all square plus C by S plus omega n, that is equal to 1 by S minus omega n divided by S plus omega n all square minus 1 by S plus omega n. Next we can find out the value of C of t by taking the inverse Laplace transform. So we have these values. So the inverse Laplace transform will give the values such that 1 by S has an inverse Laplace transform 1, and omega n divided by S plus omega n all square will have a inverse Laplace transform. Omega n is a constant, and S 1 by S plus omega n all square will give the Laplace transform t into e raised to minus omega n into t. and 1 by s plus omega n will have an inverse Laplace transform e raised to minus omega n into t. You can see the inverse Laplace and Laplace transform of 1 equal to 1 by s, Laplace transform of t into e raised to minus at equal to 1 divided by s plus n whole square, s plus a whole square, and e raised to minus at, Laplace transform e raised to minus at equal to 1 by s plus a, and here the terms are like this. So we can find out the inverse Laplace transform like this. Okay, so c of t equal to 1 minus e raised to minus omega n into t into 1 plus omega n into t. That is the response. So in the case of a critically damped situation, the response will be like this, and we can substitute different values for t. So we can plot the response curve, and this response c of t will be, in the case of unit step function, for a step input of a, we will get the step response as a into 1 minus e raised to minus omega n into t into 1 plus omega n into t. So we can plot by substituting different values of t. We can plot the response like this. We know that the input signal is a step input signal, and the corresponding response will be looking like this. That means we can find that there is no oscillations present at the output or response. In the previous cases, that means in the case of undamped case and underdamped case, there are oscillations present at the response, but in this case oscillations are reduced. That means for critically damped case there will not be any oscillations in the case of second order systems. Okay, so next is the response of the overdamped second order system for unit step input. And first of all, we can start with the transfer function of the second order system, that is c of s by r of s is equal to omega n square divided by s square plus 2 delta omega n into s plus omega n square. And for overdamped system, we know the value of damping ratio as delta greater than 1. That means we have discussed it later, that we have discussed it in the previous sessions, that when the delta greater than 1, then the roots are of the denominator of the transfer functions are real and distinct. Let the roots of the denominator be SA and SP. We can write the SA and SP is equal to minus delta omega n plus or minus omega n into square root delta square minus 1. You know that here these roots are obtained by taking the characteristic equation, that is s square plus 2 delta omega ns plus omega n square equal to 0. That is the characteristic equation, and we can find out the solution of that characteristic equation. That means if as square plus bs plus c is the equation, then its roots can be found out by the equation minus b plus or minus root minus b plus or minus root b square minus 4ac divided by 2a. That is the equation. So we can substitute for the values of a, b and c, and we will finally get the value of sa and sb as minus delta omega n plus or minus omega n into square root delta square minus 1. That is equal to, in this term we can take a minus term outside, so that we will get a sa and sb equal to minus of delta omega n minus or plus omega n into square root delta square minus 1. That is equation. So SA and SB are negative, so we can find that S1, let S1 equal to minus SA and S2 equal to minus SB. Then we can write S1 will be equal to plus delta omega n minus omega n into square root delta square minus 1, and plus S2 will be equal to delta omega n plus omega n into square root delta square minus 1. So this is just for avoiding the negative sign, that we are taking in the form S1 equal to minus SA and S2 equal to minus SB. Okay. So we got two roots such as S1 and S2. Next we can proceed with the Laplace transform of response. That is, we have the equation C of S by R of S is equal to omega n square by S plus S1 into S plus S2. You can write like this. Okay. And next, see, you got the equation of C of S by R of S like this. Here this is the C of S by R of S, and the denominator is split like this. That means the roots are S1 and S2. So you can write the denominator in terms of S1 and S2. Okay. That is why we get C of S by R of S is equal to omega n square by S plus S1 into S plus S2. Okay. So we got the equation of C of S as R of S into omega n square divided by s plus s1 into s plus s2. And here we know that step input is giving, that means r of t equal to 1. So we can write r of s is equal to, that is Laplace transform of r of t, that will be equal to 1 by s. We can substitute the value for r of s. So we will get c of s is equal to omega n square divided by s into s plus s1 into s plus s2. And next we can find out the inverse Laplace transform by partial fraction expansion method. So that first we have to write c of s in equal to a by s plus b by s plus s1 plus c by s plus s2. Next we have to find out the value of a, b and c separately. So a can be found out by, a will be equal to s into c of s at s is equal to 0. When we are substituting the value of c of s, s and s terms get cancelled, so that we will get omega n square by s1 into s2 once we substitute the value for s is equal to 0. So next we have to find out b value. See, next we have to find out here a equal to omega n square by s1 into s2. And next we can substitute the value of s1 as delta omega n minus omega n into square root delta square minus 1, that we have obtained in the first step. So also s2 will be equal to delta omega n plus omega n into square root delta square minus 1. So if we are multiplying both the terms, we will get the terms like this. So finally we will get omega n square by omega n square, that will be equal to 1. So a has a value 1. Next we can go for the calculation for b. B equal to s plus s1 into c of s at s is equal to minus s1. And when we are substituting the value for c of s, then s plus s1 terms will be cancelled out. So we will get omega n square divided by s into s plus s plus 2. And in that equation we have to substitute s is equal to minus s1. So we will get omega n square divided by minus s1 into minus s1 plus s2. And we can substitute the value for s1 and s2 as here we are keeping one s1 like that, s1, and other s1 and s2 are, we are substituting the values, so that we will get minus omega n divided by s1 into 2 into square root delta square minus 1. And next we have to find out the value of c, and c has the same procedure for finding out it, that is c of s into s plus s2 into s at s is equal to minus s2. And we can cancel the common terms from the numerator and denominator, and also we can substitute the value for s is equal to minus s2. So we will get the value like this, that is omega n square divided by minus s2 into minus s2 plus s1. So we can substitute the value for s2 and s1, and here we are keeping one s2 like that, because if we are substituting the value of s2, it will not be reduced, so that we are keeping it like this though, so that we will get the value like omega n square into omega n square divided by minus s2 into, and we substitute the value for s2 first, and then we will substitute the value for s1, so that finally we will get this value, that is omega n divided by 2 into square root delta square minus 1 into 1 by s2. So we got the values of a, b and c, and we can substitute in the value of c of s, that is c of s will be equal to, we have the equation that is c of s is equal to a by s plus b by s plus s1 plus c by s plus s2. We can substitute the value for a, b and c, and we can find out a c of t by taking the inverse Laplace transform of c of s. So we will get a c of t will be equal to L inverse 1 by s plus 1 by s minus omega n divided by 2 into delta square minus 1 into 1 by s1 into 1 by s plus s1 plus omega n divided by 2 into square root s square minus 1 into 1 by s2 into 1 by s plus s2. The inverse Laplace transform of first term is 1, and when we are taking the second term, these quantities are constants, so we are keeping those quantities there, and 1 by s plus s1 will have the Laplace transform is the Laplace transform e raised to minus s1 into t. So we can write it here, and here also omega n divided by 2 into square root delta square minus 1 into s2 is a constant term, so we can keep it there, and 1 by s plus s2 will have the inverse Laplace transform, that is e raised to minus s2 into t. And these common terms can be taken outside, so that we will get the equation c of t equal to 1 minus omega n divided by 2 into square root delta square minus 1, and other rest of the terms are e raised to minus s1 into t divided by s1 minus e raised to minus s2 into t divided by s2. So in that equation we know that S1 will be equal to delta omega n minus omega n into square root delta square minus 1, and S2 will be equal to delta omega n plus omega n into square root delta square minus 1. So this is the equation for the response in time domain, that is C of t. And in this equation we can substitute the values such as t equal to 0, 1, etc. and we will get the response like this for different values of damping ratio, such as 1.5, 2, 3 at a different time t 0 to infinity will give the response like this. And here we can see that in the case of overdamped cases, second order systems, once we draw the response, we can find that there is no oscillations in the response, but the amplitudes of the response is lesser comparing to the previous case. That means response have no oscillations, but it takes long time for the response to reach final steady state value. That is the conclusion. So we have studied about second order systems response for unit step input, and we are considering 4 cases. The first one is underdamped case, second is undamped case, third is critically damped case, and fourth is overdamped case. And in all these situations the better response is obtained in the case of critically damped case, and in the case of undamped case there are pure oscillations. You will get a sinusoidal wave. In the case of underdamped case, in the case of underdamped case you got the response, and it's some extent is oscillating, it is oscillating in to some extent, and when we are using critically damped case there will not be any oscillations, and it reaches steady state at a particular value. And when we go for overdamped case, and there will not be oscillations, but it reaches the steady state value by taking a long time. So that is the conclusion in the case of second order systems.